In this video, we're going to look at why side-side angle does not work to prove triangles congruent, and then we're going to see a special case of where it does work in what we call HL, or hypotenuse leg. So we're dealing obviously with a right triangle there. So let's look first of all at why the SSA doesn't work. And so we're going to pull up a little diagram here. We see here that we have angle A in this top diagram is held constant, and side AB and BC are also held constant, so they have to stay the same length. We see that if we take C and swing it down here so that it's on ray AD, we have a nice triangle formed. But the problem is, if I take that and keep swinging it until I get to here, once again, C is on ray AD, and we have a triangle formed once again. Both of those triangles have the same two sides, BC and AB, and angle A. But they obviously are not congruent triangles. And so that's why side-side angle doesn't work, because we can have the possibility of having more than one triangle formed with those same two sides and an angle. Our special case we want to look at is the case of hypotenuse leg. So here I have the angle formed is a right angle, and we have segment GH and segment HI held constant. So I can swing I down here so that it's on ray GF, and it forms a triangle. Well, if I keep swinging it in this case, it hits again over on the opposite side. Well, are those two triangles congruent? Well, yes, they are, because it's just the same exact thing but swung over to the other side. And so we have hypotenuse leg. So if the hypotenuse of a right triangle and one leg, hypotenuse would be HI, the leg would be HG, are held constant, and we have the right angle, then the triangles formed will be congruent. So there are some other theorems that are used with right triangles, but all of them can be done with theorems that we already have, so we don't really need the special right triangle theorems for those. And now moving into lesson 4.6 itself on isosceles triangles. So we need some terminology first. We need to know what an isosceles triangle is. And so if the angle formed by the two congruent sides in an isosceles triangle is called the vertex angle. Of course, an isosceles triangle is a triangle with two congruent sides. So where those two congruent sides come together is the vertex angle. The other two angles are called the base angles. The congruent sides are called legs. And the third side is called the base. Okay, so we can construct a congruent triangle, or an isosceles triangle, very easily by just taking a compass, starting with a line segment, and open your compass up to something more than half the length of that segment. It doesn't matter exactly what it is. And if we make an arc above the segment, and then go to the other end point and make another arc that crosses that one, then we're going to have two segments that are congruent, because the distance we measured from the points at the end of the base are the same distance from that base. So if we take that and we do a little measuring, and I find that the first angle here is just a little more than 50 degrees, it looks like. Now, I didn't draw that very accurately, and that one is just a little more than 50 degrees. So that suggests what's coming up about the base angles of an isosceles triangle. So we can conjecture that we think that the base angles of an isosceles triangle are congruent. And in fact, that is the case. According to theorems 4, 9, and 410, I've combined them together into one theorem that we'll call the isosceles triangle theorem. Two sides of a triangle are congruent if and only if the angles opposite those sides are congruent. And so, of course, our if and only if here, making this reversible. So if the base angles are congruent, then we know that the sides opposite those angles are congruent. So in symbols, for the first diagram here, I have congruent segments, and that implies that the base angles are congruent. And in the second diagram, I have congruent angles to begin with, and that implies that the opposite sides are congruent. So when we're talking about the side opposite the angle, if I'm looking at angle C on the top one here, side AB is the opposite side. And if I'm looking at angle B, then side AC is the opposite side. Down in the bottom, if I'm looking at side AC, the opposite angle is angle B. If I'm looking at side AB, the opposite angle is angle C. So always going across the triangle there. So that's going to allow us to do quite a few interesting things using that isosceles triangle theorem. So the first thing we want to do with that is prove the first part. Okay, well, what was the first part? Going forward on that, it was if two sides are congruent, then the angles opposite those sides are congruent. So here we're given triangle ABC, and AB, segment AB, is congruent to segment AC. And D is the midpoint of BC. So there is our given. So as we've seen several times already, the basic idea here is we want to prove some angles congruent, so we're going to do that by proving some triangles congruent. So since we have D a midpoint, we can put in a segment AD, and we know that segment BD is congruent to segment CD. By the midpoint theorem. Mr. Theroux would have just used the definition of congruent. I like to use the midpoint theorem there. And that's a 2 over there, not a 3. Okay, so mark that on the diagram, of course. And then we see that segment AD is congruent to itself, AD, by the reflexive property. And so, well, that circle missed. And so we have the two triangles congruent. Triangle BDA is congruent to triangle CDA by side, side, side. And then we can finish it up with angle B congruent to angle C, and the reason, of course, is corresponding parts, congruent triangles are congruent, CPC, TC. So we've proven the first part of the isosceles triangle theorem. Here then we have an application of the isosceles triangle theorem. We're given some congruent segments, DE and DC. Remember, we don't trust the diagram there, even though those don't look congruent. They are, since the statement says so. And BC congruent to AC, and angle CDE is 120. Well, we know that the angles of the triangle on the right have to add up to 180, and we know angle DCE is congruent to angle E by the isosceles triangle theorem. So that means we have 60 degrees to split between those two angles. So each angle is 30 30 degrees. Using vertical angles then, we can get that angle BCA is 30 degrees also, which leaves us 180 minus 30 is 150 degrees to split between the two remaining angles. So that means that angle CBA is 75 degrees, and angle CAB is also 75 degrees, which is the angle we wanted. So the measure of angle BAC is 75 degrees. And a couple of corollaries. Of course, a corollary following easily from a previously proven theorem. So a triangle is equilateral if and only if it is equiangular. That's just kind of a repeated application of the Isosceles triangle theorem. So if we have all three angles are 60 degrees, then pick any two and the sides opposite those have to be congruent. So if I pick the bottom two, but if I pick the two on the right, the sides opposite those have to be congruent also. And with a little bit of transitive property there and some substitution, we can get all three of those sides congruent. And we can reverse that. If the sides are congruent, then it's equiangular also. So that means if an equilateral triangle is equiangular, then each angle must have a measure of 60 degrees. So a couple of corollaries following directly from the Isosceles triangle theorem. And just applying that here with the triangle GHF is equilateral. And so we know that it is then also equiangular. And the measure of each angle has to be 60. So we have the 3x plus 4 has to equal 60. And 6y has to equal 60. And 19z plus 3 is 60 also. So I'll let you work out the values of x, y, and z there. So pause the video here and find the measures of angles 1, 2, 3, 4, and 5. And you should have found that angles 1 and 2 are both 65. Angles 3 and 4 both have measures of 35 degrees. And angle 5 is 110 degrees. Okay, and there we end lesson 4.6.